Как дела? Хорошо? Очень хорошо. Конечно, Алина. К сожалению, я не говорю по-русски, so this talk will be in English. Я плохо говорю по-русски. К сожалению. And so today we'll talk quickly about rendering in general, but most of the talk will be focused on WebGL. So basically fasten your seatbelts because this is going to be a bumpy ride. So how do we do computer graphics in the web frontend? Well, technically I'm not telling you anything new because there is already a very, very famous, very, very well-known graphics API that is the DOM. So we basically say, hey, give me a button, or give me a box of text, or give me, I don't know, an input field, which is doing computer graphics because we tell the computer what it should render and then it displays something on the screen. Terrific. And then we have CSS, which there were talks about yesterday, which were brilliant. Even though I did not understand the word, I actually understood the slides, so that was pretty great. By the way, if I'm speaking too fast or unclear, then just let me know. So yeah, we have CSS and we can actually influence how the browser does these things. Because when you say, hey, give me a button, we get a button that looks different on every platform, which is good and bad. It's good because it's actually consistent with the platform we are on. Like a button on iOS looks slightly different than a button on a Windows 95 computer. It looks different than on a Windows 8 computer. It looks different than on Android. But we might want to have more control over what we're actually getting onto the screen, so we can use CSS for that. That's cool. And I'm here to basically just tell you all these things and you're like, what the hell is this guy doing there? I could give that talk. I mean, I know CSS, I know the DOM. What the fuck? So, let me just quickly say there's a few things that you should know when you do this. Do not do layout thrashing, which means change the parameters on how it looks on the page and then read it back, because then the DOM can't be clever. Do not use inner HTML because it involves string parsing that is inherently slow. Use create element, create document fragment, and template element. If you don't know these things, definitely look them up. Also avoid CSS changes that trigger layouts often, because then the browser has to recalculate a lot of things. There's a website called CSS Triggers where you can see when changing what property, what happens, which is pretty great. Also avoid complex CSS, blah, blah, blah. And here comes the interesting bit. Canvas. Woo! Canvas. Who here has used Canvas before? Awesome. Who here likes chocolate? What? Okay, who here likes vodka? Beer? Seriously, a lot of people are either still drunk from the after party or just checking emails like, whatever, this guy is talking English, I don't care. Fair enough. So here we have an API that gives us even more flexibility, because this means we're getting a bunch of pixels that we can directly write to. Awesome, so we can actually draw all sorts of things and we can scale things, and we have a very perfect API to manipulate pixels on a pixel level, which we couldn't do in CSS unless you use a lot of divs, which is a bad idea. So here, for instance, we're just drawing a rectangle in red onto this canvas. Cool. So this is a bit better. Guys, like, yeah, computer graphics, pixel things. But there's a few problems. So if you have used Canvas for complex things, for really, really complex things, large image processing, for instance, or basically if you try to implement Photoshop in a canvas, you may at some point hit these problems. For instance, if you have a large number of draw calls, that means you draw a lot of things in circles, like a lot of lines or a lot of pixels in pixel by pixel basis. That's getting slow as fuck. You can also use scaling and rotation, so you can rotate all the things and you can scale them, and you can load images and scale them up and scale them down. You can do the same with videos, but that's also slow. It's okay if you do that for like 1 or 5 or 10 images. It also goes fine if you do it for small images, but if you do it for large amounts of objects, if you build games, for instance, if you move around a lot of objects, then it actually gets pretty freaking slow. There's techniques against that, so you can, for instance, use multiple canvases to actually contain the changes. So you have one canvas where you just have a scrolling background, and you have one canvas where there's only the players that you have to redraw, so they get a little faster. And you can also try to basically keep the amount of pixels you change very, very small. And then you're kinda okay, kinda. So I can say, well, that's all. You know, I told you how to make it fast, now go off and make it fast. You go to your office, you try to make it fast, and it's not going to get fast. Why? Well, let's have a look. So, here I have a little bit of code that basically, imagine we have an image of certain dimensions, and we just have it a couple of times. Let's say this is 100. So for 100 times, we are taking a random position on the screen and a random size. So we size it randomly between something between 0 and 512 pixels, and then we draw it on the canvas at a random position and in this size. And then we run this. And what happens is the larger the amount of stuff gets, the slower it gets. So here we are seeing, if I have one image, we're actually running at 60 frames per second. That means it actually gets redrawn 60 times per second, which is cool, which is nice and smooth. If I have 100, ooh, 30-ish. If I have 250, I'm at 20 frames per second, and so on and so forth. So it actually goes down really quick. And the shit is that we actually want 60 frames per second, because that's the only thing that is really smooth. Imagine doing something in VR or 3D, you definitely want 60 frames per second. If you do not do 60 frames per second, at least when you do virtual reality rendering, you have a serious problem because your people will actually vomit. That's a bucket full of fun. Not that it happened, but it happened in our office actually, which was not so nice. Anyway, so yeah, what can you do? I mean, now we have the canvas, which was promised to us as the fast way of actually getting pixel access, and it's not that fast, in fact. So a lot of game engines switched over to our new hero. So first of all, we are very unhappy, like, oh, goddammit, the canvas is not as fast as we want. We can't really do nice 3D graphics, we can't really do nice games, we can't do medical image processing. So what shall we do? Well, the problems are, basically, the canvas can't be fast. Well, it is fast, but it's not that fast. And it can't really be fast because most of the stuff happens in JavaScript. So we get access to the pixels, but to actually write something into the pixels, we do JavaScript, which is cool. I like JavaScript. However, it is single-threaded, so that means you have one value at a time. And if you think about it, there's a few million pixels that we have to draw in if we want to draw an entire frame in HD. That's a bit of a problem, because actually that's like, I don't know, 2.6 million pixels or something like that. It's a lot of pixels. So we don't have parallel access because we have to do all our calculations in JavaScript, and then basically the graphics card is really fast, but we do all the things in JavaScript, which is not a good idea, right? Because JavaScript is already busy. JavaScript has to do all these things like event handling, layout handling, it has to process user inputs, it has to draw shit for us, it has to also manipulate pixels and maybe calculate the scale of an image or something, and then it gets slow. Holy moly, what are we gonna do? So the other thing is, the good thing is there is something. What is it? Is it a bird? Is it a plane? No, it's WebGL. And WebGL is basically a twist where we also use the canvas, but we do things slightly different. So in WebGL, what we do is we have the canvas and we have WebGL contacts that uses the graphics card, and the graphics card actually does all the heavy lifting. And all we do is basically tell it where to go. It's basically the equivalent of a guy sitting in the sofa having a beer, yelling at people to do stuff for him, which is nasty, but actually nice for the guy. So in this case, we are the guy, so that's actually kind of convenient. So it looks like this. Because the graphics card is really, really good at drawing. The CPU is not so good at drawing. And even worse, JavaScript is not particularly good at parallel data processing. Maybe changes when we have single instruction multiple data, but we do not have that yet. So we have to wait for the graphics card to actually do stuff. If we just basically overload all the stuff to them, which is nice. And this is how it looks. I'm just kidding, don't read this, it's online. So this is a bit of a problem because it's a lot of stuff, right? But don't worry, it's actually not too bad. So how does that actually work? First things first, it works really nice because we get 60 frames per second whatever. I tried it with 10,000 and it still got me like 45 frames per second, so it goes, yeah, whatever, and the cool alien just typing away at his keyboard. And we're happy, we're like, yes! But then again, you know the API is tricky. But why the hell is it so fast? So we said, yeah, sure, we basically get a parallel pixel access, but how does that actually look in practice? Well, more or less it looks like this. And that's pretty cool, isn't it? Note the fact that this is actually marketing material from NVIDIA. So, like, yeah, sure, NVIDIA, you wish. Mythbusters was awesome. And it does that by basically shifting away most of the work from JavaScript. So here the blue box is what happens in JavaScript, the green boxes all happen on the GPU. So in JavaScript we say, hey, I have this bunch of points that you have to draw. So for instance, 3 points for making a triangle, or 1,000 points for making I don't know, model of the latest Tesla or something like that. And then I say, hey, yo, graphics card, take that into your memory. In graphics card terminology, a buffer is nothing else than just a bunch of memory. We're going to see that in a second. It's going to pass this into a vertex shader, which is a program that takes these points, can do calculations on the points in parallel, and then puts it into the fragment shader, which actually takes all these points and colors them in. So this one says where to draw. Like here we say, here we want to draw. Then we have the possibility to have a program that actually also changes the points that we want to draw, and then this one colors them in, and then we have a sparkling rainbow. Hurrah! This also works for 2D graphics, as we'll see in a second. So here's the most important vocabulary. Whenever you actually read stuff in WebGL, you're going to come across a lot of new words, because people love to invent words, because they then sound very smart. You can like, well, I just buffered all my vertices, and they go, ooh, you must know what you're doing, good sir. Well, they actually don't really know what they're doing, and that's fine. So a vertex is just a smart person's way of saying it's a point where 2 lines meet. Very cool. So it's a point, really. A buffer is just a bunch of memory. Fair enough. A shader is nothing else than a program, or actually a function. We're going to see how that looks in just a second. So having heard these words, I'm going to use them in the future. If you get confused, don't worry. I'll try to re-explain them when needed. And this is the pipeline again with a little more detail. So it's a little more boxes than it has been beforehand. Again, this blue box is the JavaScript box. All this happens on the GPU, which is nice. And then there's this weird red box. It's red and not blue because this code is actually not written in JavaScript, but written in a C-like language called GL slang, or written out GLSL, or GL shader language. Sweet. So what happens? So we give them a bunch of points. We put them into memory on the GPU for fast access. Cool. Then it's run through a program that we can write. And this program can change the points. So for instance, if we remember our example, we scaled an image, right? So we take an image and make it larger or smaller. That means we're basically just moving around the points. We have the original points here in memory, and we just say, okay, cool, let them be whatever they are, but we're gonna move them away farther from each other. So we scale up, or we move them closer together to scale down. So this can happen in this shader. Why is that good news? The good news is, it's taking data that's not gonna move, it's not gonna change. And it's not changing the data, it just changes the output on the screen. So it's independent. That means it does not have the problem of the CPU. The CPU has the problem that sometimes a function moves something, and then this other function, or the next round of the function invocation, has to use the new value to actually calculate the next one. This does not happen in shaders. Shaders get the data from memory and just pipe it through, and they don't give a shit about the other points. So I get a point, I move that around, and I'm just taking the next point and I'm moving that around. And if there's a lot of shaders, a lot of me people here, then they're just going to do that in parallel, and they're just going to pipe through all the points in parallel. Which at 4 points doesn't make that much of a difference, but if you have like 1,000 or 100,000 points, that makes quite a difference. And then the next cool thing comes, because the graphics card actually does work for us. So in the canvas, if we do not use the line primitive that we're having, we would have to calculate which pixel is inside the triangle or outside of the triangle, for instance. The graphics card can do that for us automatically, which is convenient, because we don't have to do that. And it basically figures out which pixels it has. Yes? Was that a question, or is that just stretching? Okay, so it's just stretching. Okay, fair enough. It's early, that's fine. And before lunch, I'm the last one keeping you from having lunch, sorry. What was I about to say? Oh yeah, yes. So it basically figures out which pixels we have to color in if you want to color in a triangle or a sphere or a circle or whatever. And it tells the information which pixels to color into the next program, which is called the Fragment Shader. And then the Fragment Shader can figure out what color to put in. The easiest thing is we basically just say, hey, we want a green triangle. So the Fragment Shader will go like, yeah, whatever, I'm just gonna, every pixel that I'm giving, I'm gonna make it green and put it onto the screen. Which is cool, but we can do more complicated things. We can do things like, the shader can, the fragment shader can, for instance, go like, okay, so this is my shape, and here's light coming from there, but the shape is like rotating. So right now the light is full, so I make it bright green, and now it's turning, so I make it darker green, and you can calculate that within the fragment shader, and then you put out pixels. Okay, so I've been talking a lot about shaders and fragments and stuff, so what does that actually mean? So first things first, the fragments and the rasterization. We have a bit of a problem, right? So we have these 3 points. They're clearly marked points on the screen. That's easy, fair enough. It's called our vertices or points. Cool. And we want to connect them. If we connect them, we get perfect lines. However, they're too perfect because pixels are not perfect, as you can see. So this pixel here is absolutely inside the triangle, no discussion. This pixel here is absolutely outside of the triangle, no discussion. But what about this pixel? It's kind of in, like, mildly in. This one is a bit more in, but not perfectly in. This one is also pretty okay in. So do we have to calculate that crap? No, because the graphics card can figure it out for us and actually do this math for us, and then tells us, hey, you have to color in these pixels. And by the way, I'm not going to do the work for you. And if you give me a color, I'm not making it as bright in this one because it's not fully in. I'm making it slightly less bright here, and I'm making it fully bright here. So the graphics card actually takes away this pain from us as well, which is nice. So again, shaders, we have 2 types of shaders. You always have to have both because in the pipeline you need both. So basically they are functions because they do not have side effects. And, well, ish. We're going to see that in a second. But they can be executed in parallel because you do not depend on the results of the other shaders technically. So what we get is we give it this point and we get a new point. Cool. We can do things like scaling, rotation, moving things around, warping things, changing the shape of something, all that works without having to touch memory in JavaScript. Then we have the fragment shader. It gets a screen position, actually a position really, a material, and can have all sorts of additional information. But basically, we give it the color that we want it to have, maybe light, maybe some image that it has to put onto this shape, and then it does the magic for us. And you can do things like map to grayscale, change the colors, invert the colors, make it brighter, make it darker, scale the, or sorry, not scale the texture, but you can scale the texture, but switch colors, change colors entirely, or just drop colors, or make things transparent where they weren't transparent before. All sorts of that can happen in a fragment shader. You can do waves and stuff, and it's really weird. So basically what happens is we have 2 function calls, right? So we have our 2 shaders, function 1 and function 2, and they give us a new value, and that value gets put on the screen rather than in memory. Fair enough. So here's how such a shader for scaling would look like in a very, very simple way. First things first, semicolon is not a debate, right? Semicolon would die. Very simple. Not like JavaScript, where some people go like, you can write it without semicolons. No, you can't. And then there's arguments that waste everyone's time. Please don't be that person. Use whatever you feel is right. I don't care. Oh, so where is it? Oh, how did it move? When did it move? Whatever. Fine. So first things first, we get the position. We get our point from JavaScript. That's the buffer part, right? The buffer defines which point I'm working on, so I get a point. These in vertex shaders are called attributes. Ignore that word because it's just inventing new words to screw with everyone. It's just a variable that gets passed into our function. Full stop. End of discussion. And there's another variable that gets passed into our function. The difference between these two is I can have like 16 of these, and I can have an unlimited number, well, not unlimited, but a really large number of these. So that's basically just the difference. So here we have our point, and here we get our next variable that tells us how much we actually have to scale it up or down. Cool. And this is why I said it doesn't have side effects, it's actually alive, because it doesn't return anything, but it has a side effect, a defined side effect though, where it sets this global variable to a certain value. And the value that it sets, in this case, you take the original position and multiply the position is basically x, y, z, or x and y, depending on if you do 2D or 3D, and multiply that with component-wise with the amount of scaling that you want to do. Just to give you an example, just imagine we have 1 point It's a very simple thing. It's a one-dimensional screen, which we do not have. And let's just bear with me here for a second. We have one point at -1 and one point at 1. So the difference, the distance of these 2 points is 2, right? -1 and 1, 2. So what happens if I actually just say like times 3? So then I have -3 and +3. So now these two are actually 6 pixels away from each other. So we have scaled it. It's 3 times as long. We have scaled it by a factor of 3. So that's just everything that we need to scale an image in the vertex shader. Cool. That's not too bad just yet. So we just get a new position and we are done here. In the fragment shader, I could be, oh, actually I have an example. Okay, well, very well. Did anyone not understand the example of how scaling works? Who did understand it? I know who's checking their phones. Cool. So, yeah, we just scale. And here we actually see why that's different than what we do in JavaScript. So on the left-hand side, we have the canvas 2D where everything has to happen in JavaScript that we want to make happen. And here we have shaders doing their work as well. And we say, we have these 4 points. Please scale them down for us. Will ya? Both go to work. JavaScript has moved the first point. The shaders have moved all the points. The shader is done. Well, oh look, JavaScript has finally caught up. Thank you very much. Good job. Cool, but we still have this issue of that. I don't want to write that just to actually draw a white triangle because this is what the code does. It literally does nothing else. It just draws a white triangle. And it's missing parts, so it's not even the full source code. The problem here is that the WebGL API is built on the OpenGL API. And if you have worked with the OpenGL API is very verbose, just as I said OpenGL 5 times in a single sentence. So it is very, very redundant. It keeps repeating itself, and it's actually stateful as well, and that's very annoying. The good news is there's a bunch of frameworks and libraries on top of it. Three.js, Babel.js, Babylon.js, Pixelite, all that. And I'm going to show you an example of how that works in Three.js. That's not correct, but nice anyway. Yeah, that's better. Let me get into full screen. So this one basically takes away a tiny little bit of setup effort. In Three.js you have the concept of a camera, a stage, or a scene, and objects, or meshes as they call it. So basically what I'm going to do is I'm going to more or less, so yeah, you can say I shoot a movie. I have a camera that films the scene, and I put actors on the scene, and then things happen, and then I have a movie. So let's add the box. Simple enough. So as I said, objects, as in something that I can put on top of the screen, are called meshes. What is a mesh? Well, a mesh is basically a bunch of points and how they connect to each other, which is called a geometry. So here I can say I want a new box geometry, and I make it sufficiently large. And the material. Now what does material mean? Material means what color does it have? Does it have an image on it? Does it reflect light? Does it not reflect light? Is it shiny? Non-shiny? And I'm going to say, I'm going to use the simplest one, and I'm going to use a mesh basic material. Basic means I'm just going to ignore light entirely and just can't be bothered, which is fine. So here we go. I give it a color, say green, for the nice 90s feeling. And as I say, I have to put it onto the scene for the camera to pick it up. So I'm going to put my box. This is the playground effect. So basically there is a variable called scene, which is a 3D scene. I don't want to type it all the time, so I actually basically did it automatically, and I can now use it, which is convenient. And then I get this. And this is freaking boring. This is probably the least exciting demo I've ever done. I can maybe spice it up just a tiny little bit by showing you what it actually does behind it. Yeah, that was cool. That's a legit German word, but it does not make any sense to code from this. So here we see which lines it actually sort of tries to draw and then fills in with the shaders. It's still not very interesting, so what we can do is we can move it around. We can, for instance, say, so this function is automatically called on each frame, hopefully 60 times per second. We'll hope. And it has so the box has a rotation, which is the absolute rotation in degrees at the point in time. So we can basically change that, and we want to rotate. So we have the 3 axes, we have the x-axis, we have the y-axis, and we have the z-axis. And if I want to turn it like this, I have to turn it around the y-axis, so I change the y-axis. Now this runs 60 times a second, so, and it's actually not using degrees, it's using radians. So any value from 0 to 2 pi, 6.28 something something. So I'm going to do, you know what? So this would be a half rotation. That's quite fast, 60 frames per second. So I'm just going to slow it down a little, and then I have a rotating tube. Hurrah! I can also change the geometry if I just wish to into something more interesting, like that's the least useful thing, but it looks funny, so I'm just going to go like, yeah, whatever. I can never remember the parameters, so I'm going to remove them and use the default, and then I get this. Yeah. You say I would say ew, because I think it looks like pile of poo, but sure. No, just seriously. It looks a bit like crap. Anyway, so I'm not going to contest that. So going back to our box, I can also do things. So there's the thing. Shaders are clever and actually can take whatever pixel data they get. What produces pixel data? A webcam. Ooh, that's nice. So someone actually created this thing called I hope it's this way. It's the Webcam Texture. So what can I do with the Webcam Texture? Well, I can say, please put the colors that come from the webcam onto this box. So you're going to remove this, so it's going to be this one. And then on each frame, please refresh the data coming from the video. And then it doesn't work, because probably it's written like this. Yes. And here we go. And then I can do things like, help me, I'm a child. Oops, that was wrong. I can also do things like, I don't know, I can never remember. Let's see which way it flies, the wrong way. Okay, fair enough. Whoa, like, it should move faster than it looks like. Actually, that looks more dramatic if I just do like, trapped in space, lost in space forever. Well, you can also load all sorts of 3D formats in this one. You can do more complex things, and you can build games in this. So this is 3JS, rather simple. It also has a renderer for, how the hell do I get back out of my full screen? It has a renderer for WebGL, so there's a lot of cool stuff happening. Right. Oh, Google Slides always give me a heart attack when you do that. Cool. So I hope that was not too much in not too much time. If you have any questions, wait, вопросы?
У нас вопросы. Если кто-то хочет, может задавать на английском или русском. Если на русском, я переведу.
Не понял. I understood that you said they should ask the questions in English because I do not speak Russian or something along those lines.
They can also ask Russian, I just translate.
Хорошо, да. Давай. Давайте.
Микрофон.
So he's asking about, is it real in currently to find any job in WebGL?
Yes, definitely. So first things first, WebGL is heavily used in any gaming library that you see on the web. So all of them, like Phaser.js, Pixie.js, they all actually try to get WebGL if they can. We are using WebGL in production at Archeologic, so we do WebGL visualization for people. And basically all the PR industry now gets onto that as well. So even if you're not on WebGL, OpenGL is basically the same. So if you know OpenGL, then you can get it on WebGL.
Can you just say what are you doing in your job as WebGL? That's really interesting.
Fair enough. I'm just noting that you asked for it, not me. It's a shameless plug, but this is what we do. So 20,000 years later, what we offer you is a loading bar. That's not too bad. So you give us a floor plan of your apartment, of your office, of whatever you have. This, for instance, is the apartment for Madeline, if you have noticed. And we create this model, and in the model, you can basically walk around. It's still loading, I'm sorry for that. The thing is, this is desktop, and it basically behaves as desktop, but the internet connection is slower, so it actually takes a little more time because it loads high-resolution textures. So this allows you to then, for instance, go and say, I don't like this table, or do I like this table? I don't. What the hell is wrong with the internet here? Okay, fair enough. This doesn't load that quickly. But I could change the furniture, I can move around the furniture. Oh, look at that. It did things. Let's go into the furniture library. Furniture library died, however. It's nice. Что это? Почему не работает? What you can also do is you can change the architecture, so I can drag the floor in here and change the angle, move around a little bit over here, close this one, in a little. Oops, where am I? I lost myself. Then you can move things around, make them larger, you can put walls on it. Basically, you can do architecture in all sorts of ways, right? It's more or less like Sims, yes. And we can play around. I can export this into VR applications. I can walk through this with an Oculus Rift. Architects use it to talk to their customers. Architects also use it to this one does not like it. I never understand this one. Architects understand this one, and I'm like, yeah, whatever. It's random numbers to me. Yeah, you can just play around. You can also, wait a minute, let me see if I have one. You can also do something fun, which is, where it is. You can import 3D models, which is freaking funny. But I have to find one. This is going to be a little tricky to find, but I'll try my best. I believe this is the one. Actually, no, I take the other one. So this comes from, what's it called? Wipeout. So I can drop in, I'm not logged in. Am I logged in? I think I'm logged in. So you can import 3D models into this one. Unless the internet is really slow, because it's actually converting this one in the cloud. So yeah, we have an importer, we have an exporter, we have all sorts of weird things. We have a scripting engine in here, so you can actually write your own programs to change things around. Right, it's going to take ages because it's a pretty large file. So yeah, it's basically just that.
Everything is budget.
Yeah, everything is budget. That's entirely web.
Okay, awesome. Yep. Mobile web.
Ah, good that you asked. So, mobile web browsers, including iOS's Safari, have WebGL enabled, which is cool, which is nice. And if you have to be careful a little bit because certain things are not as fast or not working as well. For instance, compressed textures are a great way of saving bandwidth, but they're actually really, really slow to decompress on mobile. So what we're doing is we do some tricks, like for instance, we have our own texture format for mobile, so that we do not have to do decompression on mobile. So mobile is just fine. Fun fact, on iOS it works slightly better than on Android, but on Android it's okay. Yeah, don't even ask me. I just nod and smile and like, that's unusual, but iOS works better than Android. My personal opinion. So mobile web is just fine, you just have to make sure that you understand the memory constraints and the problems that it brings with itself.
We have changed to play games on mobile.
Absolutely, yeah.
And it's fine.
Yeah. It's not going to look as good as on desktop because you have to reduce the quality. But if you do that, it just works fine. Good question. For games I have not seen problems yet, but I can imagine that if you do like really heavy things where you can't downgrade the quality, then the data might or will definitely be faster. But the difference is really minimal because, for instance, Chrome and Safari, I'm not sure about Safari, but Chrome basically runs a native process with OpenGL and just pipes the data through, so it does not do much than just passing data. As I said, if you, for instance, try to, today's, God, what's it called? I forgot the name of it. It's a photo editing app that actually runs entirely in the browser. It's more or less what Photoshop Express did, or Photoshop Elements, I think it's called originally. So you can basically use that for if you have a very high resolution image, like 10,000 by 10,000 pixels, for whatever reason, you have like a raw image that you actually want to import, and you want to scale it, and you want to change the histogram, and you want to change the color scheme, and you want to maybe do some tracing of shapes and stuff like that. You can do that on the GPU, but you can only do that on WebGL. Weird and unusual application. There was people trying, in the very early days, there were people trying to mine Bitcoin. Which is an interesting proposal, but it didn't work because you can't really have the complexity that you need in WebGL shaders. They are blacklisting you when you do that. Weird applications. So there's a bunch of VR applications that are quite fun to watch. Weird applications. Not that many weird applications. It's fun applications. Like there's a photo booth app that uses WebGL to do the transformations.
Yeah. Микрофон можно использовать, не слышно бывает. Спасибо.
Can you programmatically detect the current frames per second, for example, for the mobile platform, in the user device can produce only 20 or 40 frames per second? It would be great to reduce the quality of the text or something like that, just to avoid the gaps in slideshows.
Can do that. If you notice, there's this little thing on top of here. It's very, very small, I know, but it says 60 frames per 50 frames per 59 frames per second right now. So you can definitely detect that and then downgrade dynamically. The thing is that due to the nature of how WebGL looks, you actually lose a lot of time when you do that dynamically, because it's not very easy, it's not instant. So you would have to unload the shaders and load new shaders, which takes time and have to be compiled in line and that. So it's not as easy, it's not as helpful, but you can definitely do that and then disable features. Follow-up question.
Okay. More questions?
Later.
All done? Now we have the microphone. Thanks for advice.
Have you faced some situations where you thought some main WebGL code should run fast, but it runs slow, and like, have you had to write some workarounds for that?
That's called my day job, yeah. No, actually that's not true. We have really, really clever people who know much more about shaders than I do, and they do magical things as well. So yes, that is a problem. Particularly, the biggest problem is WebGL 1, as it is standard right now. WebGL 2 is around the corner, but WebGL 1 is based on the OpenGL ES3, I believe. So that's really, really old, so you do not have all the shader functions. For instance, you can't use certain texture formats, you have to do that yourself, and that's annoying. You cannot use vertex buffer objects, which means you can't just put data in and then put data out and put it into the buffers. Like, you do not have a full feedback loop. You can do that with the tricks, but it's not that easy. And you have to do a lot of optimizations for mobile as well, so the shaders have to be optimized for mobile if you want to do it right. And yeah, it's not always easy. For instance, we figured out, basically no one told us that compressed textures is slow on mobile. We didn't know that. We just noticed that it is perceivably slower than on desktop. So we basically disabled that and used JPEG textures, which is okay, but we still had frame drops on older phones. And that's why we thought, why the fuck does that happen? What is making this slow? So we built a few prototypes and noticed the slowness does not come from rendering or from the shaders or from the textures themselves. It comes from the fact that the gzip textures come in and then have to be basically still, they're JPEG, so they are also compressed. So you have to decompress that and recalculate the pixel values, and then you shift the pixel values, throw half of it away, and put it into a texture. That is inefficient. So we built our own texture format that basically comes in as gzip, raw data, and then we just pipe it into memory, and we do not have any frame drops anymore. Like, we have literally 10 times the performance that we had beforehand with complex textures, and we have twice the performance that we have with non-complex textures. So we have to actually dig in, but you have tools for that. So there's Webgl Inspector, and then there's Webgl Insights that basically give you a possibility to see what's happening on the graphics card. So yeah, we have to optimize it.
More questions? You said about Webgl Inspector, so this is a tool for debugging. So
yes.
What about debugging this, like how it's can be done?
So, as I said, there's this very, very handy extension. I don't have Webgl Inspector installed right now. Don't ask me why. I'm as surprised as you are. So this is a Chrome extension that allows me to see certain things. So for instance, let's actually render something. Oh shit. I'm gonna make it stop moving, because if I make it moving, then it's actually not very interesting to watch. So we have the Webgl Inspector here, sorry, insights here. So for instance, sometimes when you're not careful enough with optimizing your scene, you may actually draw multiple times on the same spot. So you can click here and you see, green. Green is good news because that means this pixel has not been really drawn. If this would be red anywhere, I would know that my shader is probably broken because it's drawing the same pixel multiple times. That shouldn't happen. I can see the bitmaps for textures. This one does not have bitmaps, so that doesn't work. I can see how far away things are. That's also not very interesting. Well, actually, wait a second. Maybe Archinogic is actually a better example. If it wouldn't just be trying to process something. You can see how far away things are from the cam, because we had weird bugs. We had the issue of so you can, when you're in this mode, you can still select things like this furniture piece. Well, however, I can't select it right now, but theoretically I can select it. And the problem was picking. So basically, we have to cast a ray from the mouse pointer from the camera to the mouse pointer to figure out which thing you clicked on. And there was an issue with the depth map, so that means that it pretended to be farther away than it actually was, and it picked the wrong thing. Let's see if that actually does the right thing. Yes. And then you can see how far away things are rendered, and sometimes you have errors where this is really, really helpful. You can actually pause each frame, so now I do a drag, and then I can go. So I can see each frame being drawn individually. Okay, I'm going to drag a little more, and do this again. You can see, did you notice something? I moved the entire way, but it wasn't actually going like one by one. That's because we optimized this kind of stuff. You can profile things, like for instance, I can see when it switches between shaders. I can see when it actually calls shaders twice. I can get the call stack of draw calls, and I can then just take a profile snapshot, and then, oh right, now it actually didn't do anything because I didn't do anything. That was not very clever. So let's record a profile. I'm doing something here, stopping the profiling, and hopefully this time the computer doesn't crash, because this laptop is not my work laptop, so no, it didn't crash, that's good. But it actually takes ages to load the profile, that's terrific. Alright, I'm really, really happy that this is not my work computer. So here we now see what happened in WebGL, how long did it take, what were the arguments, right? And what call was it? So here we bind the buffer. This means we say which object we want to draw. We enable its points in the shader. We draw that. Then we put some uniforms in, and we change another uniform that is a matrix in this case. So we actually get a call stack and all that nicely as we need it. You also see the shaders. So these are the shaders that we're using right now in this particular scene. This is one vertex shader, slightly longer than my example, just slightly more. So you can actually debug these. You can actually see the actual state. As I said, this is stateful. So you see which texture it's right now trying to touch and work with. You see all the settings, all the flags. You see the resources it's using. You see the textures it's using. There's a bunch of them, just transparent textures for reasons that are tricky to explain right now. But then we have like, oh, that's data textures, damn it. I need one that's not a data texture. I think this one might be one, no? Okay, this is still loading, fair enough. Here we have it. I don't even know where this material is, but it's probably the floor. So you can see the textures that it's using, you can see all the buffers, so all the vertices and all the things. This buffer does not exist anymore, so you can actually check it. So this is actually really, really helpful. When I implemented caching in our application, I needed to know when it actually gets cleaned up, and sometimes it got cleaned up incorrectly. This was really, really helpful to find that. Do not use that many frame buffers unless I pause them, so you have frame buffer information, you have the render buffer information. You have a lot of information and you can disable the thing if you just get fed up with it. So Then there's the other thing, the Webgl Inspector allows you to basically set breakpoints in your shaders and then go one by one, which is also really handy. So debugging is fun.
Awesome. More questions? No? Okay.
Do you have any Easter eggs in your app?
You can jump.
That's cool.